Hey there, fellow mathematicians. Welcome back to recitation here in Math 141, Summer 2020. As always, it's your TA Bailey here. Today we are on episode 4, and we are giving an ode to one-directional limits, talking about what makes you continuous as we look at sections 2.4 and 2.5. 2.4 looks at one-sided limits, and 2.5 looks at continuity. These two ideas are very closely related, as the notion of continuity, the definition, really depends upon these one-sided limits. Now, in some sense, continuity is very simple, right? Continuity is, can I draw the curve without picking up my pen or my Apple Pen or my pencil or whatever device it is that we're using, right? In some sense, continuity is very simple in that way. But in another sense, continuity is kind of tricky in that how do we rigorously define this, right? In a real math textbook, a very formal one, we can't just say, yes, can you draw it without picking up your pencil? We have to give a more rigorous definition involving inequalities, equations, and things like that. And so that's part of what makes continuity so interesting to me. And continuity is also going to be one of the most important ideas throughout the remainder of your mathematical career. So, without further ado, let's get going with some problems. There's a whole lot that I want to do today. I have 8 problems picked out, so let's get going on those. The first one is, so we are going to be given, let me write it this way. Rather than starting with find, let me start with, so let f of x be x plus 10 times the fraction x plus 7 absolute value over x plus 7. And then we want to find the limit as x approaches minus 7 from the positive side of f of x, and the limit as x approaches minus 7 from the negative side, from the left-hand side. Now, oftentimes, these two limits are the same, whether we approach our point, in this case, negative 7, from the left-hand side or the right-hand side. And if that's the case, that pushes us in the direction of continuity. In fact, there's one more condition that needs to be true in continuity, but that pushes us in that direction. However, in this case, it is going to be important which side we approach negative 7 from. So let's get going, and let's first look at what happens whenever we approach negative 7 from the positive side. Well, the key observation that we're going to make here, and this is why it's important whether we're approaching from the positive or negative side. Well, here we're only interested in x greater than negative 7. So if x is greater than negative 7, it might be just a teeny tiny bit bigger, right? It might be like 7.00000001. But as long as it's bigger, no matter how much bigger, well, if x is greater than negative 7, then x plus 7 is going to be greater than 0. Right? You can see that by just adding 7 to both sides of this first inequality. This means that the absolute value of x plus 7 is just equal to x plus 7 in this case, right? For example, the absolute value of 2 is just 2, because 2 is positive. Okay, so with that in mind, we can see that the limit as x approaches minus 7 from the positive side, okay, well, f of x was x plus 10 times absolute value x plus 7 over x plus 7. Well, now we can replace, in fact, what we can do is we can drop those absolute value bars. Negative 7 from the positive side, x plus 10, right? Because we know now that for these x on the left-hand side, the right-hand side of negative 7, the absolute value of x plus 7 is just x plus 7. Okay, so now that is super helpful because now this fraction is just a 1. And so this just becomes the limit as x approaches -7 from the positive side of x plus 10. And at this point, it doesn't matter whether we're coming from the positive or negative side. We can just plug in -7 to find that our limit is 3. So this we found by plugging in x equals -7. Okay, so for this first limit, it was important that we knew that we were approaching from the right-hand side because that led to the nice observation that we could drop those absolute value bars. Now, what happens if we approach it from the other direction? Well, let's find out. So if we look at the limit as x approaches -7 from the left-hand side, okay, well, in this case, so if x is smaller than -7, again, it could be tiny, hardly smaller than -7. It could be wait a minute. What I said earlier, I said 7.0001. I should have said -6.999999. Rather, I was getting my positive and negatives confused. So in this case, even if x is like -7.00000001, it doesn't matter as long as this inequality holds. Well, then x plus 7 is going to be less than 0. Right, just add 7 to both sides of our first inequality here. And what does that mean? Why is that relevant? Well, that means that the absolute value of x plus 7 is going to be negative x plus 7. Right? In this case, the analogy is that, well, -2, the absolute value of that is -2, which is just 2. Okay, so with that observation in hand, limit as x approaches -7 from the left, x plus 10 times absolute value x plus 7 over x plus 7. Well, now I'm going to replace that absolute value with a negative sign, x plus 10, and I've got negative x plus 7 over x plus 7. So before, we could cancel this fraction out as a 1, but now we have to cancel it out as a -1. And doing that gives us limit x approaches -7 from the left of now negative x plus 10. Excuse me, I just saw a silly mistake up here. This should say -7 plus 10. I'm not sure where the 3 came from. I guess I knew that the final answer was 3 and I skipped a step. Sorry about that. It's just a small typo and misspeako. Okay, coming back to where we were. So now let's see, I get limit x approaches -7 from the left. If I just distribute that negative x minus 10. And now, just as before, I am ready to plug in my stuff. So if I plug in x equals -7, then I get -7 is 7, minus 10 equals -3. All right, so this is just x equals -7 is how we did that. And so our answer here, -3, is not the same as our limit up here. And so this isn't actually part of the question, but it's worth emphasizing here. So I'll mention it because this is an important part of continuity in this whole discussion. So since the limit as x approaches -7 from the left is not equal to the limit as x approaches -7 from the left, since this is true, that since these two are not the same, f is discontinuous at x equals -7. okay? Now, if these two were equal, that wouldn't quite be enough to say that it is continuous, but because it's not equal, we know for sure that it's not continuous. There is one other condition which needs to be true in order for the function to actually be continuous at that point. But I think we'll talk about that in a later problem. The next problem which I want to do is problem 10. I didn't get any requests for this video, which is okay. I do certainly like requests. It makes my job a little bit easier, to be honest with you. Because then I don't have to worry as much about picking which problems to do. But also, I just want to make sure that I am being as helpful as possible. So please continue to send me things if there are things that you want to see. In this problem, we are going to use the fact that the limit as theta approaches 0 of sine of theta over theta equals 1 to find, so we're going to use this fact to find another fact to find the limit as, let me see, theta goes to 0 of sine of theta over sine of 6 theta. Okay, so we are reminded of this very nice fact, which we have seen now, hopefully in the video or in Mackenzie's video or in the textbook. Okay, so we know that this we know this limit, and we want to use that limit to find this other limit. The problem is that I don't see anything here that looks like sine of something over something, over that same something, right? Like in this relation which we're supposed to use, there's very clearly sine of something, theta can be whatever, over that same something, but I don't see that here. But what I can do, well, surely if I multiply this by 1, then nothing will change. That should be 6 theta. And what I'm going to do is I'm going to multiply by 1 in the form of 6 theta over 6 theta. Now, why am I going to do this? Because now, look at what this will give me. This will give me sine of theta times 6 theta over sine of 6 theta times 6 theta. And this, I can break it up because limits are super nice, you'll recall. So then this, I can split this up into the limit as theta approaches 0 of 6 theta over sine 6 theta times the limit as theta approaches 0 of sine theta over 6 theta. Okay, so all that I've done is I have used the nice multiplicative properties of limits to split this up. And now let's consider each of these pieces in turn. So let's look at this left-hand piece first. Let's look at this, the limit as theta approaches 0 of 6 theta over sine of 6 theta. Well, this very much looks like our identity. We've got the 6 theta and the sine of 6 theta. The problem is that they're flipped, right? So in this identity at the top, we have the sine on top. But here is what I notice. So again, going back to the nice properties of limits, the limit of as theta approaches 0 of 6 theta over sine of 6 theta, well, that is going to be, how do I want to write this? 1 over the limit as theta approaches 0 of sine of theta over 6 theta. In other words, what I've done here is I flipped my fraction. All right, so I've just taken the reciprocal. So I can flip that fraction and then put a 1 over that entire limit. We're basically just using the multiplicity of limits here. And now this limit, I know that the limit of sine theta, that should be sine 6 theta. So this limit down here, I know to be 1. And so this is just 1. Okay? So what I can do is I can flip, here I flipped both the limit and I flipped the fraction. Now if we look at the second part of our equation here, well, if I look at the limit as theta approaches 0 of sine theta over 6 theta, well, I can rewrite this as 1/6 times the limit as theta goes to 0 of sine theta over theta. Right, this 1/6 is just a constant that's hiding in this first and this one over here on the left. So I can factor it out of the limit. And now I know that this second limit here, this limit sine theta over theta is 1, which means that this comes out to 1/6. So now, going back to where we were, we find that our limit here is actually just 1 times 1/6. And that, we know, is equal to 1/6. So that is our limit. Okay, so let's recap. We could not immediately use this relation because we did not have something of the form sine of something, over that same something. But what we could do is we could introduce this 6 theta in order to give us something that looked like, well, it didn't quite look like sine of something over something, but it did look like something over sine of something, right? I'm talking about this right here, where we had 6 theta over sine of 6 theta. And so what we could do is we could flip everything there, and then we were able to use the sine of 6 theta over 6 theta. Okay? You might be asking, well, Bailey, the relation up here says sine of theta over theta. So why does it still work if we've changed theta to 6 theta? Well, the important thing is just that it's something, right? If I wanted to, I could let x be 6 theta. Well, then this is just the limit, and notice that as theta goes to 0, x also goes to 0, because x is 6 times theta, so if theta becomes 0, then x becomes 0. So then, this is just the limit as x goes to 0 of sine of x over x. And this is just the same identity, just with a different variable. So that's why we are allowed to do that. Again, the important thing is that it is sine of something over that same something, and we need the limit of that something to go to 0. Then for the second limit here, the sine of theta over 6 theta, well, we could just pull the 1/6 out and then use the same relation. Okay? Okay. 2 problems down, a good 6 to go. Let us get going on problem 7. I'm actually going to jump backwards a little bit because this idea, which we just used here in 10, is actually going to be very helpful here in 7. So again, we are told to use the relation limit as theta goes to 0 of sine theta over theta equals 1. So use that to find the limit as x approaches 0 of tangent 9x over x. Okay, so this time, at least last time we started with a sign. Here, we're not even given any signs to get started with. So universe, come on, give me a sign. But well, I can rewrite this. I can rewrite tangent as just sine over cosine, right? So this is sine of 9x over cosine of 9x all over x. And I can bring that cosine down to the denominator. X approaches 0. Sine of 9x over x cosine 9x. Okay, so this seems like a pretty good start. Now again, I have sine of something, and I would love if I could have that same something in the denominator. I don't quite have it here, but I do have an x. So rather than needing to multiply by 9x over 9x, what I can do is just multiply by 9 over 9. And whenever I do that, it goes to 0. I'm going to get 9 sine 9x. Oh, that 9 should be in parentheses as well. 9 sine of 9x over 9x cosine 9x. Okay. And we're going to do this is what I was talking about, how the other problem is actually going to come in handy here. Because we're going to split this up and do basically the same thing that we did before. So that's the limit as x approaches 0 of sine of 9x over 9x times the limit of, let me see, I'm left with a 9 in the numerator, cosine 9x in the denominator. Well, this first limit, sine of 9x over 9x, that's going to be 1. Okay, basically the same ideas we just used. The second limit now, this one looks tricky. It looks like I'm going to get a 0 in the denominator, but actually, so if I just plug in x equals 0, well, cosine of 0 is not 0, it's 1. And so this just becomes 9 over 1, or 9. Okay? So this time, we broke down this tangent and wrote it in terms of sines and cosines. That was our starting point. We then multiplied by a fancy looking 1 up here, right? We multiplied by 9 over 9 so that we could eventually get something like sine of something over that same something. From there, we were able to eliminate that part as a 1, and then everything else we were able to take the limit of as usual, i.e. just by plugging in the value. This problem demonstrates a very important trick, which I'm going to emphasize, which I really want to emphasize. Let me write it out here for you. So if we are, when given a problem with, so if I have a problem with tan or secant or cosecant or cotangent, sometimes it's easier, not always, but sometimes, like in this case, it's easier to break things down into sine and cosine. Break down into sines, not that kind of sine with a G, sines, not sins, and cosines. This is a very important idea. Again, I just want to emphasize this. This I'm sure will come in handy throughout this course. I know in Calculus 2, which I've TA'd for the last 2 semesters, it's come up quite a bit. And in general, whenever I have problems involving trig functions, I also find it easier oftentimes to break things down into sines and cosines. Now, I would try to do it first using whatever trig functions you're given, because sometimes things do work out more easily that way. In fact, later today we'll see a problem in which it works out very nicely with tangents and secants. But if you feel stuck and you don't know where to go, this can be a great way to help break out of it. So much of math is really just learning how to get yourself unstuck. Okay, so now let me step down from my soapbox and step into problem 16. Problem 16 asks to determine the points, well, point, and then in parentheses asks, because maybe it's just one point, maybe it's more than one, I don't know. The points at which, okay, so the function is f of x equals root 9x plus 27 is continuous. Okay, so determine the points, or maybe just a singular point, at which this function is continuous. Now, as I kind of alluded to at the beginning of this episode, continuity itself can actually be kind of a tricky definition. It has a few different pieces which can sometimes be tricky to check and can also, quite frankly, require a little bit more work than we would like to do to check. So we would love, whenever possible, to be able to do things a little bit quicker. Thankfully, in this case, we can do that. So if I let g of x be 9x plus 27, and h of x, that's an h, let me redraw that, and h of x equals root x. Well, these two functions are both continuous wherever they are defined. Okay, g and h are continuous wherever they are defined, or in other words, on their entire domain. So on entire domain. That's one of the nice things. So we know this is true about polynomials. That's why we know that this is true. And the root x one is kind of just a special one. We know that all of the roots, x to any power is going to be continuous, and this is just x to the 1/2. So it is certainly continuous as well. Furthermore, we know that compositions of continuous functions are continuous, which means that, let me see, so h composed with h of x, let me write it this way, h composed with g, not hog, h composed with g of x, which is exactly equal to f of x, by the way, right? If I start with g of x, that gives me 9x plus 27, and then I apply h of x, so I get square root of 9x plus 27, which is exactly what f of x is. Well, that means that this function is continuous over its entire domain. Continuous over entire domain. Therefore, this problem reduces to finding the domain of f. So we just need to find domain of f. And this is something which we've been doing all summer now. We've been doing it since section 1.1. So we've really broken down this complicated 2.5 problem back into something from section 1.1. So that's a great thing. So let's find that domain. Okay, so let me again write it so we don't have to keep scrolling up. So f of x is root 9x plus 27. Well, the only thing that we have to look out for here is that we need 9x plus 27 to be greater than or equal to 0, as otherwise we're going to be trying to take the square root of a negative number, and that's not going to work. So I need 9x plus 27 to be greater than or equal to 0. In other words, I need 9x to be greater than or equal to negative 27. In other words, I need x to be greater than or equal to negative 3. Therefore, f is continuous on, so our interval for our domain is going to be minus 3 to infinity, and we are including minus 3. And so that gives us our set of x values over which the function is continuous. Okay? Fantastic. Let us move on to problem 17. Halfway done with the problems I wanted to cover in this video. So problem 17, 17, 38. 17 says, it's the same type of question. At what points is, in this case, we have y equals 6x minus 4 to the 1/3 continuous. And so again, we see that this is just, so y is the composition of 6x minus 4 and x to the 1/3, which if you'd prefer, you can write as the cubed root of x. They mean the same thing. Those two functions are both continuous, just like we talked about with the previous problem, which means that y is continuous on its entire domain. So you may be thinking, that's strange. Why did he choose to do two problems in a row that are basically exactly the same? But here is the twist. The twist now is that, so before we had to figure out where our we had to figure out where 9x plus 27 was greater than or equal to 0. So here the question is, well, for what real numbers does the cubed root of that real number exist? And the answer to that question is all of them, right? So x to the 1/3 exists for all real x. Think about it. For example, the cubed root of minus 1 is minus 1. So this demonstrates that even the negatives do have cube roots, which means that the domain of y is all real numbers, minus infinity to positive infinity. And as we said a moment ago, the domain of y is exactly where y is continuous. So that tells us where y is continuous. All real numbers. This guy is continuous everywhere, and I think that's pretty dope. Good for you, y. Keep it up. Okay, so this problem was basically the same as the previous. We noticed that our function was a composition of two functions which we know to be continuous wherever they are defined, which means that y is continuous wherever it is defined, and in this case that happens to be everywhere. Now, I'm not going to do problem 18 because it's very similar, but I do want to clarify some notation. Hopefully, you'll be comfortable with this. I'm sure you've seen it at some point, but if not, just a refresher for you. So x to the 2/3, what that means is, well, there are two ways of looking at it. I can look at this as the cubed root of x, all of that squared. Or if I prefer, I can look at this as the cubed root of x squared. These two things are these two things are both the same, and the notation x to the 2/3 can be used for both. So the question which I pose to you, and rather really which your homework is going to pose to you, is, let me write it this way. For what real numbers x does x to the 2/3 exist? Right, so remember that x to the 1/2 only exists for non-negative x. X to the 1/3 existed for all x. So how about 2/3? I will leave that to you to ponder. And you should, of course, feel free to reach out if you struggle or have any questions about it. I believe that will be relevant for problem 18. We are now going to jump to problem 21. And 21 says to find the limit. Find the limit. There are actually two parts to this problem. The second part I'm going to leave to you. All that you're going to do is use this information that we find in the first part to answer a yes or no question. So we'll find the limit, and I think you'll be in good shape then for the second part. Now the limit that we're looking for is the limit as y approaches 1 of secant, and now in parentheses, so secant of y times secant squared of y minus tangent squared of y minus 1. Oh my goodness. Good golly, Miss Molly, look at this thing. I've got trig functions, secant squared, tangent squared, inside a bigger trig function, this bigger secant. Oh my goodness. Well, one of the nice things about limits is that we can bring this limit inside, like so. So I can bring it inside the secant. So now I have y secant squared y minus tangent squared y. Here we're really going to draw upon the litness of limits, i.e. their very lit algebraic properties. And so now what I can do is I can distribute this limit across addition, right? So now I'm going to have the limit as y approaches 1 of y secant squared y minus the limit as y approaches 1 of tangent squared y minus 1. No need to take a limit of 1 because that's just 1. Okay, well now I can further break up this first one into the limit as y approaches 1 of y times the limit as y approaches 1 of secant squared y minus the limit as y approaches 1 of tangent squared y minus 1, close parentheses. I think I have an extra parenthesis, but that's okay. Yeah, I do have an extra. Okay. And now, I think, in some sense, it looks like I'm making things a lot more complicated, but actually, we're going to see that now it's pretty straightforward, because now, okay, well, this first part, the limit as y approaches 1 of y, well, that's just 1. Okay, now the second limit, y approaches 1 of secant squared y, so that's just secant squared of 1. Right? Both of those we got just by plugging in y equals 1. They work out very nicely. Similarly, for the tangent one, I'm just going to get tangent squared of 1. And then I still have this minus 1 at the end. Okay, well, I can get rid of this first 1. No need for that. So secant squared 1 minus tangent squared 1 minus 1. Golly, I still have these secants and tangents all over the place. That's kind of a pain. Until we either remember or learn, depending on your background. Maybe you've seen it, maybe you haven't. The lesser famous trig identity, that secant squared theta minus tangent squared theta is equal to 1. This is kind of like the Kevin Jonas of the trig identities. Everybody knows and loves sine squared plus cosine squared equals 1, but secant squared minus tangent squared kind of gets forgotten about. But he's still important. And here we can use this guy to rewrite this secant, to rewrite this argument here. Well, secant squared minus tangent squared is 1. So this is just 1 minus 1. And so that's just 0. Okay, I don't know much about secant, but I do know that secant is 1 over cosine. And cosine of 0, that guy is 1. And so this is just 1 over 1, which is 1. Look at that, a whole lot of algebra. And really what we did here was we took advantage of the trig identity that secant squared minus tangent squared is 1. If that's an identity which you aren't already comfortable with and familiar with, I certainly recommend getting to know him. Maybe take him out to dinner, get some coffee, something along those lines. He's going to be a fantastic resource for you throughout the remainder of your mathematical career. So get to know him, get comfortable with him. Okay, again, to reiterate, we also really took advantage of some of these nice algebraic properties of limits by distributing them to break down this really complicated limit into really just a bunch of simpler limits from this step to this step. Right? We knew how to take all these limits, which made it nice and simple from there. Okay. That is 21. There are 2 more, which I hope to do here. Not which I hope to do, which I will do, because I am in control of whether or not I do them. Nobody's going to cut me off at an hour, which I suppose is a nice thing about these YouTube videos. I don't know. Problem 22. Define g of 2. Oh, so this is a different kind of problem. So let me finish writing it, and then we will talk briefly about what this is really asking for. So define g of 2 for the function g of x equals 2x squared minus 8 over 2x minus 4. And we want the limit, oh no, wait, excuse me. Define g of 2 for the function so that g of x is continuous at x equals 2. Okay? So what is this really asking? Well, the first thing that we notice is that g of 2 is undefined, because if I plug in 2, then I see that I'm going to be dividing by 0. So g of 2 doesn't make sense here, which means that if I look at the graph, I don't know exactly what the graph is going to look like here. And frankly, I don't care for the sake of this picture. So if this is x equals 2, that means that the function is going to look something like, I'm going to have a hole here, but other than that, it's going to look something like, I don't know, that maybe. I don't know, maybe it's some sort of weirdly sideways parabola like this. The point is this hole here at x equals 2. So what we want to do, so we want to fill in that hole. To fill in hole. In other words, what is the y coordinate of that hole, Coordinate of hole. Again, we cannot just plug in x equals 2 into the function to find out what it is, because the function doesn't make sense at x equals 2. However, what we can do is we can take the limit as x approaches 2 of g of x. Because that is what this coordinate is going to be. It's going to be whatever that limit is. Okay, remember, limits don't actually care what's going on at the point itself. They care about what's going on just barely, really close around that point. Okay? So that's the idea here, is all that this question is asking for really is what is this limit? So let's go ahead and calculate it. We want the limit as x approaches 2. Well, g of x, that's 2x squared minus 8 over 2x minus 4. I'll admit I don't know off the top of my head, so it certainly looks like we're going to want to factor. Sorry about that. My pen died, and so I had to charge it for a few minutes, but we're back. Okay, so as I was saying, I don't know immediately how to factor that numerator. However, I'm pretty sure that I'm going to want to factor out a 2x minus 4 so that I can cancel it with that denominator. So I'm going to go ahead and guess that one of my two factors is going to be 2x minus 4. And now, if I look at the rest of it, I think x plus 2 will get the job done. So let me just check my work real quick. It gives me 2x squared plus 4x minus 8. Yup, that is what I want. Fantastic. And so now I can cancel out my 2x minus 4s, boom, boom. And I am left with limit as x approaches 2 of x plus 2. And that is just 4, which we get simply by plugging in x equals 2. And that is what we wanted, right? We wanted to find the limit of g of x as x approaches 2. Again, kind of similar to the previous problem, we see that we're given something which sounds a bit more complicated and more challenging. But really, we were able to just break it down into, okay, what is this really asking for? Oh, it's asking for this thing which we've done before and we've started to get comfortable with. So that gives us problem 22. And the final problem I would like to do is in a similar vein. It is problem 24. And 24 asks us for what values of a and b is the following function continuous function continuous at every x. The function which we're given is defined piecewise. And so for x less than or equal to -1, the function is defined to be -2. It is ax minus b for x between -1 and 3. So those are the a and b that we're going to have to solve for, a and b there. And then it is 12 for x greater than or equal to 3. So let's draw another picture. And in fact, in this case, we can very nicely draw a picture. So this is not going to be to scale by any means, So let me mark off. So this is x equals -1. Let's draw x equals 3 here-ish. Let's put -2 down here. And this is the part that's not going to be to scale. Let's put 12, I don't know, up here. And so our function looks, okay, so from x, so for x less than or equals -1, we're here at -2. Then for x greater than or equal to 3, we're up here at 12. And so we just need to figure out what is going on in the middle here. Now in the middle, I know that it's going to be a line segment, right? So ax minus b is a line segment. Right? If I write y equals ax minus b, that certainly looks like a line. And so since we're only looking over the x values -1 to 3, this is a line segment. So I know that it must look like this. It must be the line segment which connects these 2 points, which means that we must find, so must find A and B such that, well, I need, whenever I plug in x equals -1, I had better get that y equals -2. So in other words, I need a times -1 plus b to equal -2. And similarly, I'm going to need a times 3 plus b to equal 12. Okay, so those correspond to these 2 points. Again, because I know it's going to be a line segment, so I just need to make sure that it is connected to these 2 points in order for my function to be continuous. Okay, so how do we solve a system of equations like this? You've probably done something like this before in your mathematical career, but it can be tricky if you haven't done it for a little bit. So let's go through this in detail. Well, this second equation, I noticed, should that be, excuse me, this should be minus b minus b. So let me just fix that real quick. Okay. Well, let me start with the second equation. I noticed that the second equation, this is the same thing as 3a minus 12 equals b. Right? If I just add b to both sides and subtract 12 from both sides, then this just becomes 3a minus 12 equals b. Okay, so now what I can do is I can plug that into my first equation to see that -a minus, well now b is 3a minus 12 equals -2. And now I have an equation with just one variable, right? I only have a in this equation, so I can solve this. So minus a minus 3a plus 12 equals -2. Let me see, minus 4a equals minus 14. And then this becomes a equals minus 7/2. Okay, I did that part kind of quickly, the algebra. But the nice thing about YouTube, you can take your time, pause it, do the algebra yourself if you need to. But regardless, we get that a is -7/2. And now I plug this back into my equation for b, and I get that 3 times -7/2 minus 12 equals b, right? Just plug in this value of a here. And that gives me -21/2 minus 12 equals b. Excuse me, I think that I have a typo. I do have a typo, I knew it. A should be positive 7/2, so that becomes positive, positive. There we go, now we're talking. Okay. And so now this becomes 21/2 minus 12 equals B. Well, 12 is 24/2, so this becomes minus 3/2 equals B. And now I have my values of A and of B. And so that does it. That gives us our solution. All right. That is all that I wanted to cover in episode 4 here. I hope that all of this made sense. If not, please ask me questions, shoot me an email. I suppose you could post it in the comments if you would like, whatever is best for you. If there's anything you want to see in the next video, please let me know about that. Otherwise, I hope that you have a great rest of your day. Whether you're watching this at night or in the morning or whatever time, I hope that the rest of your day, whatever time it is enjoyable.